Hello everyone, welcome to the course VLSI Design Flow RTL to GDS. This is the 10th lecture. In the previous lecture, we had looked into a few constructs of the Verilog language that will help us in modeling an RTL or writing a behavioral description of our design. In this lecture, we will be continuing with more such constructs that will help us in writing a Verilog model, right. So, modules are basically the basic building blocks for Verilog design. It starts with the keyword module and ends with end modules. So, we have module, within this we write everything and then there is an end module. So, within this module and end module we write the code for a module, right. So, this is the basic, though there can be many modules in our design, and modules are basically the most important building blocks of a Verilog design, and modules are instantiated inside another modules to create a design hierarchy. So, instantiation of a module means using that module in another higher level module, right. Let us take an example. For example, if we want to create a design hierarchy like this, there is a top, then inside this we have a mid, and then also we have bottom, and inside this mid we have another bottom. So, we can create this by writing modules. We can write module top, right, and inside this module we have two instances, mid of this one and bottom 2, right. So, these two are the instances within the module top. So, mid is the name of the module, right, which is being instantiated. Instantiated is a kind of saying copying the everything in whatever is there in another module into this module, right. And M1 is a name of the instance. This is an arbitrary name that we can give, right. And then the other modules, for example, mid contains bottom 1, right. So, the mid contains bottom 1. So, there is another module mid, and inside this there is an instance bottom 1 whose name is B1, right, and bottom 1 and bottom 2 are there which do not contain any other modules, right. So, those are leaf level modules. So, in this manner we can have a module and several instantiation within that, and the instance of one module can refer to another module, and the other module can again have other instances and so on. This way we can create a design hierarchy in a form of a tree. Now, let us look at how we can define ports in a module using Verilog. So, ports are basically the interfaces of a module, and it allows communications between the module and the environment. So, ports can be declared with the keyword input, output and in-out in a Verilog module, right. It can be scalar or vector similar to net and reg, right. So, for example, in this case we are saying that there is a module top and the ports are this, right, ports are defined and their directions are defined here. So, some are scalar ports and some are vectors. Now, let us understand how we can define instances in Verilog and their connections. So, connections for an instances can be specified in two ways. The first one is by order. So, or it is a kind of implicit connection. So, in this case ports connected automatically in the instantiation based on the order specified in the module declaration. So, what it means is that suppose there is a module mid, right, it has got ports clock, D in, D out. We want to instantiate this mid in the module top. So, what we can do is that we can write mid, the name of the module, an instance name which is arbitrary, say M1, and then we define the nets which is going to connect each of the ports. So, C will be connected to clock, P in will be connected to D in, P out will be connected to D out. So, based on the order, each net in the instantiation will get connected to the port in the corresponding instance or pin in the corresponding instance. So, ports connected automatically in the instantiation based on order. For example, if I change the order here P underscore in and then C, then P in will be connected to clock and C will be connected to D, right. So, depending on the order the connections will be made. So, this is difficult to debug. Why it is difficult? Because while instantiating, there is no information that which net is connected to which port or pin in the master or in the module, which is of the master module of the instance, right. So, in that case it will be difficult to debug if there are some problems in the connections, right. And here it is only 3 ports, right, but in real designs you can have 100 ports in a module, and then it will be really difficult to understand which net is going to which port in the instance if we do instantiation in the implicit manner or in the order by order. So, the other way to do or define connections for instances is explicit connection, right. So, in this case ports are connected by explicitly giving names, right. For this is an example, right. So, in this case what we say that while instantiating I say dot clock. Dot clock refers to the port in the master module of mid, right. So, this is the mid, this is an instance, right, and its master module is here, right. So, whatever the port name was there I defined here clock and then say that the net C is basically connected to clock and D in is connected to P in and D out is connected to P out. So, we are explicitly making the connection with the ports, and in this order we can define this first or last, it does not matter, the connection will always be correct. So, as far as possible we should try to use explicit connection define connections explicitly while doing instantiation when we write a Verilog code. Now, let us look at what are parameterized module in Verilog. So, Verilog allows definition of constants for a module, constants within a module using a keyword parameter. Okay. So, the module in which a parameter exists, those modules are known as parameterized modules, right. So, while defining parameter in a module, we give a default value to the parameter, and those default values can be overridden at the time of instantiation by using hash, right. So, let us take how it can be done. Let's look into it. So, suppose there is a module counter, right. So, in this module I am saying that there is a parameter width, right, and whose default value is 4, and this parameter width will be used within this module counter, right. And this probably will define in some way that what is the size of this counter depending on the parameter width, right. Now, while instantiating we can say that give the value of width as 16, right, rather than 4, or we can say that give the value of 128 to whatever the parameter is in this case, right. So, the first parameter here is width, or that is the only parameter in this module. So, 128 value will be given to width, or we do not specify the parameter value during instantiation, and in that case a default value of the parameter, that is 4, will be assumed. So, what this parameter allows, or this flexibility gives us, is that it allows us to vary the properties or the characteristics or interfaces of a module based on instantiation, right. So, the main module or the master module was having only one parameter, which is width, right, and that is for and the module contains all the description with respect to this parameter width, right. Now, while instantiating we can vary the value of width and we get different implementation of that module in some sense, right, or different variants of that module by varying the parameter, right. So, that the one module we write and different flavors we can get out of it using parameter. Now, Verilog also supports built-in gates. For example, there are keywords and, NAND, OR, NOR, XOR, XNOR, through which we can use directly in our code and use it for making logical connections and making circuits, right. So, the convention here is that the first pin is the output pin and rest are inputs. For example, suppose I use a primitive gate or built-in gate of Verilog, and A1 is the instance name, and then we give Y1, A and B. So, this one is the first one is the output pin, right, output pin, and the rest are input. So, it is something like this, you have A, B and this is Y1, right. So, this way we can get the instantiate, or we can instantiate built-in gates in our Verilog code. Now, Verilog supports operators and expressions also, similar to other programming languages such as C. It supports arithmetic operators like plus, minus, etc., logical operators, bitwise operators, relational operators and shift operators. So, these are some of the operators which are supported by Verilog. Now, operators act on operands to produce results, right, and these operands can be of various data types such as nets, variables, bit select, part select or array element, right. So, operators can act on all these data types, and the number of operands for an operator is defined by the language. For example, there are some with one operand only, right. For example, a not operation, it involves only one operand, right. There can be there are some operators which take two operands, for example, less than. Then there are operators which take three operands. For example, this is a ternary operator. So, we say C question mark A else B. What it means is that the value of this expression will be, if C is true, then it will take a value A, else it will take a value of B, right. So, this will be the value of this expression. Now, this takes three operands C, A and B, right. So, the number of operands that the operator can take, that is well defined by the language. Now, where we can form expressions by combining operators with operands and that yield some result, and we can use parenthesis to override the default precedence that is among the operators. For example, this is an expression, right, this is an expression A and B and a not of that, right, and then P is less than Q is another expression, X plus Y star Z is another expression. So, we have used parenthesis to override the default precedence of or greater precedence of multiplication over addition. Then there are some special operators which are supported in Verilog. Let us look at a few of them. So, one is called reduction operator, and it takes it takes only one operand. It takes a single operand to produce a single bit result, and the result of it is only single bit, and it will take one operand. Okay. So, these are reduction operators, these are logical operators, and it operates bitwise on the operand, and finally, it will give one bit answer, right. So, the computation starts from LSP and moves to MSB bitwise based on what the reduction operator is used. For example, suppose A is an operand whose value is 1011, right. So, what it will do is that if we write AND A, that is the reduction operator AND over A, it will first take the AND of the LSP 1 and 1, right. So, the answer of that will be 1, right. Then it will take the second one 0 and 1, the answer will be 0, right. Then it will take the third one 1 and 0, and the answer will be 0, right. So, the final value of y will be 0 in this case. So, this is how reduction operator works. Then there is a concatenation operator which combines the bits of two or more data objects. For example, if we have A is equal of 2 bits, B of 4 bits and C of 1 bit, right. Now, if we say A comma B comma C, right. So, it using this concatenation operator, right, then it will be a 2 plus 4 plus 1, that is 7 bit wide number. First we have 2, these 2 bits, then these 2 bits and the third, right. And if we want to have many such replication or multiple concatenations, then we can use replication operator. For example, if we have A, B, C the same thing and we want to take 4 copies of A, right. So, we used 4 and then 4 number defines that you have to replicate it 4 times, right, and B, and then say 2 times we want to replicate C. So, we get 4 times replication of A, right, then B and then 2 time replication of 1 bit, right, that because C is of having a value of 0, right. So, these are some of the special operators of Verilog. Now, let us look into the block of statement. So, a group of statements within the keywords begin and end forms a block, and we can also give a name to a block, right. For example, if we say begin and end, we have these statements. So, this is a block of statement, right. We can give it optionally, we can give a name to it, my block name in this case. And what will be the understanding or how the language will understand it, or the simulator will understand it. So, it will basically execute these statements within the block, within the begin end statement in a sequential manner, right. So, whatever we put inside begin and end, that is known as a sequential block, right, all these statements. So, statement 1 will be executed, then statement 2, then 3, right. So, this is a sequential block. Then there is another type of block which is a parallel block, in which we use 4 can join, right. We use, instead of begin end, we say 4 can join, and then the statements here are executed parallelly, okay, statements executed parallelly or concurrently, and this kind of blocks are known as parallel blocks. So, a Verilog supports control statements, if else, right, case, for, while, repeat, similar to C programming language, right. For example, if we want to write a if kind of statement, we will say that if this condition is true, then do something, else do something else, right. So, this is how we can write if a conditional kind of operation, right. Similarly, if there are multiple options available, then we can use case statement, right. So, if we do case and there is cell is a signal here, right. Now, depending on the value of cell, whether it is 0, 1, 2, while be assigned either A, B or C, and if none of them matches, then a default value D will be assigned to Y. There are 2 variants of case, one is case Z and case X. So, in case Z treats Z as do not cares, right, and case X treats X and Z both as do not cares. Then there are loops, for example, for loop. So, it is similar to other programming languages. So, in this case it starts with something and does some part until a termination criteria is met, right. So, this is a criteria which is saying that when to continue this loop, right. So, it will be continued till I is less than 8. So, similar kind of looping we can do using while, right. So, we say I is less than 8, do these things, right. So, same statement written in terms of while, or we can use repeat statement. If we know that this has to be done a fixed number of time, in 8 in this case, then we can say repeat 8 and write the code within begin and end. Now, let us look into the structured procedures that are available in Verilog. So, there are 4 types of or there are 4 constructs for structured procedures. So, the first one is initial block, second is always block, third is function and fourth is task, right. So, now let us look at all of them one by one. First, let us look into the initial and always block. So, what is an initial block? Initial block is a block of code which starts with the keyword initial. And what is an always block? Always block is a block of code starting with the keyword always. Now, both types of blocks are enabled when the simulation begins, that is at time 0. But what differentiates them? So, initial block executes only once and stops when it reaches the end of the block, right? And always block executes repeatedly throughout the simulation. So, this is the main difference between initial block and the always block. So, let us take an example of that. So, here I am showing an initial block and this is an always block. So, in this initial block there are two signals, clock and counter, and where at time 0 these two signals will be initialized to 0 based on these statements, and once it reaches end the simulation will stop for this particular block. But what will happen for the always block? The always block will be executed throughout the simulation. Suppose initial value of clock was 0, right? Suppose the initial value of clock was 0, then after 10 time units the value will become 1, right? Then again after, so hash 10 means that there is a delay of 10 time units in executing this statement. So, after 10 time units it will again change to 0. Then again after 10 since we have clock here and it is a negation of clock, then after 10 time units it will again become 1. So, we will get a infinite sequence of 0, 1, 0, 1, so on until the end of simulation. Now, always blocks are useful when we have event control for them, and controlling event can be a value change on a net or value or a variable. So, there are multiple ways to do a control or to control when an always block is executed. One of them is what is known as using the value change on a net or variable, and this is known as level sensitive kind of always block. So, here we say that in this example always at the rate of enable begin reg A is equal to reg B. What it means is that whenever there is a change in enable signal, this block of code will be executed, right. So, here the event control is provided by the change in the value of the enable signal or EN signal. So, we can also define event based on the direction of change of a net or a variable, and that this is known as edge sensitive always block. So, there are two types of edge sensitivity. The first one is positive edge. So, this is a kind of sensitivity when a signal goes or transition towards 1. For example, transition from 0, x or z to 1, right. So, when it transitions towards 1, then we say that it is a positive edge. Remember that Verilog is a 4 valued logic, right. So, we have to not only bother about 0 to 1 transition, but we have to also consider the transition x to 1 or z to 1 also as a positive edge. Also, you should note that the transition from 0 to z or x is also treated as pos edge as per Verilog language, right. Similarly, neg edge is a transition from of a signal towards 0, and the transition can be from 1 x or z to 0, or it can be from 1 to z or x. All these kind of transitions are treated as neg edge. For example, if we write a code like always at the rate pos edge clock begin end. So, what pos edge means here is that whenever the signal clock will go or make a transition from 0 to 1, right, then this block will be executed, block of code will be executed. Other condition under which this block of code can be executed are based on x and z values as described in this in this rule, right. So, the there are two ways of triggering or triggering an always block. The first one is the level sensitive, where a signal changes a value, it is changes a value, then we say that the always block will be executed, as in this case. The other is there is a direction to the change, meaning that it will get triggered only when 0 to 1 transition is happening, not the other way around. For example, if it is 1 to 0 transition, this block will not be triggered. Sometimes we need to specify the triggering event as an OR of various triggering events, right. So, if that is the requirement, then what we can do is that we can separate various events using OR statement or comma, right. For example, if we want that this always block gets triggered when there is either a pause edge of clock or neg edge of reset, then we can write like this: pause edge clock or neg edge reset. So, the OR separated list of triggering events is called the sensitivity list. So, in this case there are two signals in the sensitivity list, clock and reset. Sometimes we need to put all signals read in an always block in the sensitivity list, right. When we want to do that, when we are modeling all combinational logic. So, in that case what we can do is that we can use ampersand star to indicate that that block will be triggered whenever there is a change in any of the signals which are read within that always block. For example, if we say that always at star begin and in between that we write q is equal to a and b or c XOR d or e, then this block will be triggered when any of these signals a, b, c, d, e which are read undergoes any change, right. So, if there are lots of such signals, it may be cumbersome to write all of them in the sensitivity list. So, in that case we can simply write always @star. Now, let us understand when to use the initial block and when to use the always block. So, the initial blocks are used in test benches when we do simulations. We will discuss this later in this course, and it is used to initialize our design for simulation. So, and the always blocks are basic entities which are used for modeling modeling or behavioral modeling of the code. So, always blocks are typically used to define our circuit, right, and initial blocks are mostly used for simulation or test bench purposes. So, a module can have any number of initial block and always block. There can be multiple always block, initial block, and there is no precedence between them, or all these blocks get executed at the beginning of the simulation time, and there is no predefined order in starting the execution of these initial and always block. And it also means that initial blocks need not be executed before the always block. So, initial and always block provide a mechanism to model the concurrency of the hardware. Now, why there is no predefined order? Because in terms of hardware, when there is a hardware and there are multiple hardware, then we are not sure when we apply an input where the signal will be going first and which one will start operation first, right. That kind of doing control is difficult when there are parallel operations. So, in that sense, initial and always block provide a mechanism to model the concurrency of the hardware, if anyone can start operation first, right. And that is the language has said that there is no predefined order, considering that parallel hardware works in this manner. So, as a designer, what we should do is that we should think initial and initial block and always block as different hardware components which are working in parallel and whose order of starting the execution is not within our control. And this behavior, and this is important because simulator or simulation tool is free to choose any order, right. So, we should ensure that by choosing any order of execution we get the correct result, right. So, the result should not depend on order of execution of the always block. in a given Verilog module. Now, let us look into functions and tasks. So, functions and tasks can be used to model repeated codes. So, the function starts with the keyword function and ends with end function, and task starts with the keyword task and ends with end task. So, let us first understand the differences between functions and tasks. So, a function can have one or multiple inputs, at least there should be one, right, and it should produce only one output, while task can have 0 or multiple inputs, and it can also have 0 or multiple outputs or inouts. Now, functions cannot have delays modeled as pause edge, neg edge or hash delay, while task can have delays modeled by pause edge, neg edge or hash. And functions are used to model only the combinational circuit, while task can be used to model both combinational and sequential circuits. And functions can call another function, but cannot call another task, while task can call other task as well as function. So, these are the most important differences between functions and tasks, and let us look into the uses of these structures. So, this is an example where function is used. So, there is a function within a module. The name of the function is myfunc, right, and the inputs are x, y, z. So, there are 3 inputs, and the output is x minus y plus z, and it is assigned to myfunc, right. So, there is a signal or register which is having a name as myfunc, which can be used inside this function. And we can call this function. So, these are 2 calls of functions, and we are giving the inputs as a, b and c, right. So, these will be mapped to x, y, z in this function, right, and the answer will be a corresponding to this expression a minus b plus c, and that value will be assigned to output. So, this is what the equivalent code will be of this function call. And for the let us look into an example of a task. So, here the task name is my task, right, and the inputs are x and y, and there are 2 outputs. So, see, in this case we had only one output in case of function. Here there are 2 outputs, right, sum and carry, and these are the calls of the task, right. So, depending on what the requirement or what the repeated code is there or repeated structure we have in our hardware, depending on that we can use either function or task in our Verilog code. Now, let us look at various types of assignments in Verilog. There are 2 types of assignments in Verilog: continuous assignment and procedural assignment. Now, what is a continuous assignment? Continuous assignments provide values to nets, and the keyword for continuous assignment is assign, and it is used to model combinational circuits. So, here is an example: assign out is equal to S, if S is equal to 1, then A, else B, right. So, it is a kind of a multiplexer that will be created for out, right. Now, this is a kind of this is called a continuous assignment, and it is assigning a value or giving a value to a net which is whose name is out. There is another type of assignment which is procedural assignment. Now, what are procedural assignment? Procedural assignments provides values to variables such as reg or integer types. say, so the values that are given to these or that are assigned in procedural assignment, they remain there, right, and they do not change their values until next procedural assignment. So, values get assigned and it remains there until it is overridden by another value. So, it is used inside structured procedures, initial block, always block, functions and tasks, right. So, whenever we want to write values or assign values inside initial block, always block or functions and tasks, there we need to use res type or integer type and use procedural assignments, right. So, there are two types of procedural assignments also. One is known as blocking assignment and another is non-blocking assignment as shown here. So, if we write Q equal to D, right, that is a blocking assignment. What does that mean? We will just see, right. And if we write Q less than equal to, the symbol is same as less than or equal to, right. Depending on the context, it will be understood that whether it is less than or equal to or it is a procedural assignment, right. So, Q is less than equal to D, this is a this means that the value of D is assigned to Q in a non-blocking manner. What do we mean by non-blocking manner? We will just see, okay. So, there are two types of procedural assignment, first one is blocking, another is non-blocking. The symbol is for blocking is equal to and for non-blocking it is less than equal to, we have just seen. An easy method to remember that what is the symbol for assignment, we can think of that the blocking assignment, blocking is a smaller word and it has got a smaller symbol, and non-blocking is a bigger word and it has got a bigger symbol also. So, the for a blocking assignment what happens is that the execution of next statement is blocked until the current statement is executed, right. So, it is similar to what we do in our programming languages. So, if one statement is executed, then the next one and so on. So, it is done in a sequential manner, it is done in a sequential manner. And what happens for non-blocking assignment? Execution of the next statement not blocked until the current statement is executed, right. Though the statement is not blocking the other statements. While the first statement is being processed, the next one can continue processing and so on. That is what is done for non-blocking assignment, and it means that it is it means that non-blocking assignment somewhat models a kind of parallel execution, right. Now, let us understand a little more that what non-blocking assignment is. When we say something, say A assigned to B in a non-blocking manner, so this assignment is done in two steps. So, this assignment is done in two steps. In first step, what is done is that only the RHS part is evaluated, right. Suppose it was a complicated signal B and C or Y, some complicated expression was there on the RHS. So, whatever the value of the RHS, current value of RHS is, that is evaluated in the first step. Only the RHS step is evaluated, okay, and the execution moves to the next statement. The LHS is not yet assigned the value, right. That part happens at the end of the simulation, right. We will be understanding this more precisely in the next video. But the important thing is that whenever there is a non-blocking assignment, the execution happens in two steps. In the first step, only the RHS part of the expression is evaluated and its current value is kept somewhere, and with the intention that at the end of the simulation time I will assign the current value of RHS to the LHS, right. So, in the next step the LHS will be assigned, but the execution is allowed to continue to the next statement and so on, right. So, this is how the execution of non-blocking assignment is done. So, let us understand this using an example. So, in this module there are two initial blocks, the first initial block and the second initial block. So, both these initial blocks will start executing at time 0. Now, in the first initial block we have all the statements are blocking assignments, right, and in the second initial block all the statements are non-blocking assignments. Now, when the first initial block is being executed, then the simulator will encounter the statement A has 10, 1 tick B1. Has 10 means that there should be a delay of 10 time units, right. So, it will start executing at time 0, and the statement is saying that after 10 time units A should be assigned a value of 1. So, at t is equal to 10 time units A will be assigned a value of 1. Then it goes to the next statement. Next statement says that after 30 time units assign value of 1 to B. So, currently t was 10, so 30 will be added and t becomes now 40. So, at t time 40 B will be assigned a value of 1. Then comes the third statement which says C is equal to has 20, 1 tick B1. So, whenever there, so after a time of 20 time units, that is 40 plus 20, that is t is equal to 60 time units, C will be assigned a value of 1, right. So, this assignments has happened in a blocking manner, meaning that the next assignment do not go, or the execution do not reach the next statement until the first one has done all the processing. Similarly, it does not reach the third statement until the second one has also done the process, right. So, this is a kind of blocking assignment similar to traditional programming language, nothing different, right. But something interesting happens in non-blocking assignment. Now, in non-blocking assignment, as I said, the execution happens in 2 steps, right. So, when it encounters P non-blocking has 10, 1 tick B1, it simply says that okay, I want to assign RHS in this case is simply 1 to P, and at what time? At time 10. So, it just schedules or plans schedule to write P or write 1 to P at t is equal to 10, and after just this scheduling it moves to the next statement. It does not wait till 10 time units and till the LHS is updated, right. When it goes to the next statement, it says that okay, the RHS is 1 tick B1, meaning that it is 1, right. So, it will say that I will assign, I schedule to write 1 to Q at t is equal to 30, and it moves to the next statement, right. Similarly, it schedules to assign 1 to R at time 20 and it moves. Now, it reaches the end, right. Now, at the end it will update all the values. At time 10 P will be getting a value of 1, at 30 the value 1 will be returned to Q, and at 20 value will be 1 will be returned to R. So, as per what was scheduled to be written, the LHS will be updated all of them together, right. So, in that manner, in that sense, this PQR has been written in a parallel manner, and that is what the difference between the simulation of a blocking assignment and a non-blocking assignment. Non-blocking assignment, as we see, is somewhat modeling a parallel execution or parallel assignment of the registers or variables. Now, in addition to the constructs that we saw, the Verilog supports various system tasks and functions. So, this system task and function help us in debugging and in verification. So, the name of these functions always start with a dollar. A few examples of system tasks and functions are display, probe, monitor, stop, finish, reset, random, time, etc. Right. So, these are some of the useful system task and function, and their names are most of the time self-explanatory, but you should be going through the manuals to understand more deeply into how these system task and functions uh, behave or work like. So, these are some of the important references that I have used in these lectures, and you may go through them, right. And there are lots of materials available over internet on Verilog, and those are also quite useful. But the Bible of all those things is this the language reference manual. So, whenever in doubt, please refer to the language reference manual, and those are the most authoritative kind of description of the language. So, to summarize, what we can say is or in last two lectures what we have done is that we have looked into various constructs of Verilog, which will help you in writing a Verilog model or RTL model. Now, in the next couple of lectures, we will be looking into that how are these constructs used or interpreted by simulation and the synthesis too, because we need simulation to verify that what we have written is as per our expectation, right, and we need synthesis to get a hardware out of it. Because in RTL, when we write in terms of using the constructs that we have described, those will be a kind of behavioral model of our design in terms of how the signal goes from one registers to other and so on. The corresponding hardware or the logic or the net list out of it has to be interpreted by looking into the constructs, its meaning, and then mapping it to a hardware, and that is what the RTL synthesis is. So, we will be looking into RTL simulation and RTL synthesis in next couple of lectures. Thank you very much.